Hi, this is Dr. Liu. So we're looking at this lab on capacitors. So this is lab 4. The left side is the lab manual, and the right side are the data I collected. So let's take a look. The CK is the known capacitor. CU theory is the unknown capacitor. Uh, this is in theory, though the capacitor is marked with 2.25 microfarads, and the other ones marked with 5.69 microfarads. And when they're in series, this is supposed to be the result. You're basically taking the product of the two capacitance and divide by their sums. I'm just replacing the values by their cell numbers. So that calculates to a value less than either one of them, which is correct. And then by putting them in parallel, we're adding these two together. So let's do this value plus this other value. Okay. And this column is V1 voltage. I had V1 set to 10 volts. Make sure you check your voltage. And this is V2, which is the voltage after you charge the unknown capacitor with your known capacitor. And this is the calculated experimental um, result. This is from this unnumbered equation. The unknown is known times V1, the 10 volts, minus your measurement, divided by measurement. So let's click and take a look. So known capacitance, and then the 10 volts V1 minus the 3.3 volt, for instance, divided by that V2. In my experiment, I did two measurements of the smaller capacitors because this was, let's see, using a 2 microfarad, I barely made it to about 50% of a charge, 50% of voltage. I'm supposed to go between 50 and 30, and 1/3, right? 33% of the 10 volt, and got exactly 5 volts. So I did it again with a 1 microfarad capacitor. I got that, and I calculated both on both with the same formula, and I got roughly 2 microfarad, unlike the 2.25, so more than 10% off. And then I also did the other capacitor with a 5 microfarad, and I got a close enough value, 569,542. So roughly 3 out of 55, so that's less than 10%. And then I connected the two in series. I'm supposed to get 1.6 and I got 1.44, so 1.5, roughly 10%, close to about 10% of difference. But then when I put them in parallel, I actually measured twice, and both times I got this value. We're supposed to have the sum, which is almost 8, but my calculation yield just a little less than 6. And I checked my wiring, I checked um, basically everything, and I measured twice. So both times I got 4.1, 4.0, so that gives you 576 to 6 microfarads. So that's that. And that's basically what I got. So um, now in the report, the percent error would be between the experimental and the theoretical. So I'll do a relative error for this, for instance, that should be equal to absolute value between the experimental and theory, doesn't matter which one comes first, divide by theory. So that gives you a small value. Well, this time actually not this small. And I want to give it a percent style. So 28%, that's pretty high. And for all these other trials, between 5 and 11%, that is fair enough. All right. So that would be the relative error. And also the relative uncertainty, or RU, let's just shorten that a little so we can have space. So RU, on the other hand, is calculated based on this. So you can see the formula computes uncertainty of your unknown capacitor, and these requires quite a bit of calculation. So what exactly is the DCK? So that's the uncertainty of the known capacitor. Do we actually know how much that is? Uh, we actually don't know much about it, except that we know we have 1, 2, 3, 4, 5, up to 10 to choose from. So this one we don't actually know. And then the uncertainty of the voltages, I'm pretty sure the uncertainties can be within about 0.1 volt because the smallest divisions are 0.2 volts, and we can easily read that needle in between two smallest divisions to make a 0.1, even more accurate if you want, but at least we can do that with a 0.1. So the uncertainty here is um, is difficult to estimate without knowing how uncertain the known capacitor is. So we'll try to estimate the unknown capacitor, having an idea that maybe the uncertainty right here is about 10%. So we'll skip this, we'll calculate that first. So let's do an unknown capacitor, which is that times square root, and then this whole thing times this. So V1 squared, so V1 carried to 2 divided by V1 minus V2 squared, so V1 minus V2 carried to 2 squared, and then multiply each one of them. So dV1 is 0.1 volt uncertainty over the V1 that was read as this. So that needs to be squared. And plus dV2 is also about 0.1 volts over the V2 that was read, and then square. Okay, hopefully I have the right amount of parentheses. Okay, that ends here. I still need one for the square root to close. Okay. Okay, so based on the calculations, the uncertainty is about 11% without knowing the decay. So what I'll do is I'll give you a decay during the lab so we can add that decay to the front right here. So what exactly is this decay? Let's say a 0.0, so it takes the space, but it doesn't actually affect us. So the known capacitor is I use a 1, for instance. Square and plus. Okay, so this is at dk, dck or dc over ck squared, and then here's the rest. So currently it's just a 0. I'll give you a value once I'm a bit more comfortable giving an estimate. What exactly is the uncertainty? Okay, so it looks like the uncertainty for this particular trial is larger, and also for that is even larger. All right.